I missed this one slide by Smith on the lateral outflow. They concluded that there would appear to be scales of influence of the desert regions embedded within the larger domain in which the deserts manifest themselves as local energy sources to processes that feed back to the larger scale. In particular, feedback to processes that influence the distribution of moisture which the deserts themselves lack. So basically the heat flow and the lateral exhaust is being created by dry desert mechanisms, but then it's intruding into the southwesterly jet and modulating the monsoon moisture processes. Continuing that monsoon desert feedback then, Rodwell and Hoskins noted that the Charney's idea of this albedo feedback, where if you have desert forming and bare soils, rocks, sand having high albedo creating net heat loss in the radiation balance, and whether that could have a self-induction effect, they argued that the mechanism of desertification proposed here is that the Asian monsoon heating induces a Rossby wave pattern to its west, as we know. Integral with the Rossby pattern is descent and a thermal structure with isentropes sloping down into the monsoon region. Air on the southern flanks of the mid-latitude westerlies, so try to imagine monsoon heating, mid-latitude westerlies, and air on the southern flanks of the westerlies towards the monsoon, interacts with the warm structure and even in the absence of diabatic effects descends as it glides down the sloping isentropes. So basically this is going to explain how we're going to get additional subsidence in the June-July-August rainy season over the deserts, which looks very weak when we look at the zonal main meridional section. Okay, this model we had looked at in chapter 9 with two layers, the upper layer and the lower layer. It's a steady state model. It's a slice of the sphere that we looked at this way. We looked at this in terms of perturbation, energy generation by the waves and so on, and how the background flow basic state affects the wave dynamics. And we had looked at the stretching parameters or the regions where perturbation energy is going to go to zero, right? So you have in the westerly regimes high potential perturbation kinetic energy of the waves, whereas that tends to zero. So we're trying to see where the intrusion of the extratropics into the tropics would be most favored by extratropical breaking Rossby wave activity and at the jet exit region and so on. The same model is here used with a heating. Some heating is prescribed iteratively, and so steady state is reached. That's the steady state solution in the steady state model. So there is the heating with maximum in the center and diffusing out, and it's looking at the latitudinal and longitudinal section at 25 the heating is imposed at 25 north, and the contours here are basically vertical velocity distributions in pressure coordinate in 10 to the minus 3 Newton per meter squared per second, different unit. Before we looked at hectopascals per second, but that was 10 to the 4, doesn't matter. So we are basically on the 500 hectopascal surface, and we are looking at the heating and its impact in terms of the rising motion where the heating is, and how the heating causes a sinking motion to the west of it through this Rossby wave monsoon desert mechanism as it is known now. Okay, so this is two-level steady state described in Appendix J and Figure 9.2 together with the basic state. So this is our Figure 9.2, which showed the basic state. The model here extends pole to pole. You can see 90 south to 90 north, and the point is that the monsoon heating influence goes quite far. Not much into the southern hemisphere, but quite far in the northern hemisphere. But this essentially confirms in a simple model that Here the horizontal and vertical shears are prescribed in the steady state, which is what we were looking at here. Okay, so you can see that clearly there is a downward vertical motion to the west of the rising motion associated with the monsoon heating. Since this is at 25 north, we can essentially take it as the South Asian monsoon heating in this simple experiment, and clearly shows that the desert mechanism, and even if you go westward on the subtropical highs, they are greatly affected by this monsoon diabatic heating. So Charney's idea was somewhat incomplete. The radiation balance and the net radiative losses are important, and they do create some kind of feedback, albedo feedback, but the contribution of the monsoon itself is also critical for enhancing this subsidence over the deserts and maintaining the deserts. Okay, obviously this doesn't explain why we don't have monsoon in other subtropical land regions, and we'll see that that has much more to do with the heating by the Tibetan plateau. But again, there are debates about whether the Tibetan plateau heating is important or whether it's just an orographic barrier that prevents the mixing of the warm, moist tropical air coming from the Indian Ocean in the southwesterly jet with the mid-latitude colder, drier air. Okay, so those details we'll touch upon a little bit later on in another chapter. So this is, as I said, fairly short chapter with just the basic mechanism of radiation balance that we looked at, diurnal variability. Nocturnal jet is an interesting phenomenon. The lateral exhaust is an interesting phenomenon, and the monsoon desert link is a really interesting phenomenon. Okay, we'll leave that and then move on to the next chapter.